Okay, let's go ahead and get started. I just want to say thank you to everyone for joining us today. This is the first webinar for Bell in a series of a three-part webinar on sleep. And my name is Corinne Tucker. I'm the marketing director at Bell, and I'll also be the moderator today. So if you have questions, please put them in the chat and we'll do a question and answer session after Kyle's presentation. I want to introduce Bell scientist Kyle Morgan. Kyle is the lead author of Focal Limbic Sources Create the Large Slow Oscillations of the EEG and Human Deep Sleep. And that's the topic of his lecture today. So I'll let Kyle go ahead and take it away. Thanks.
Sorry, I was on mute. Hi, guys. So as Corinne said, my name is Kyle. We're going to go through this paper that we published in Sleep Medicine. I think it was earlier last year, but just want to say, everyone, thank you for joining us today. So we'll start off just briefly. I know there's varying levels of experience throughout this participant pool here. So I'll just go over just kind of a basic introduction to sleep and sleep stages. And this will be extremely brief. Hold on, I gotta mess with my mouse here for a second. There we go. Okay, so for those that are aware or not aware, sleep occurs in stages throughout the night, meaning it's not just one continuous thing. There are 3 stages of what we call non-REM sleep, which are denoted by N1 through 3, plus a single stage of REM sleep, which probably most people are very familiar with. Each stage has its own neurological features measurable by high-density EEG, and it's these neurological features that help us characterize each stage of sleep. So in REM sleep, it's classified by desynchronized brainwaves. It almost looks like you're awake. And then in the stages of non-REM, as you progress through them, you have these increasingly slowing synchronized brainwaves. And then as we so the stages are being increasingly understood to play different roles in recovery and other different physiological things and memory consolidation. And then as we learn more about each role of each stage, it puts increasing pressure on scientists to study the neural mechanisms associated with each stage. And we're kind of trying to paint a more complete picture of these roles. Over a century, research has definitively concluded at least one thing, and that's if you don't sleep, you don't consolidate memories. And this effect is most obvious in stage N3, which is the stage we're going to look at today. Stage N3 is characterized by large slow oscillations in the delta frequency band, which is between 0.5 to 4 hertz. Usually it's classified by closer to 1, but in reality, we found slow oscillations closer to 0.5 hertz. And these slow oscillations are associated with periods of minimal neuronal activity called down states. And these down states are important to memory in some way, and that's everything that's being debated still. On a higher level, the consolidation or memory replay process that happens during N3 sleep is thought to be mediated by interactions between limbic, neocortical, and thalamic brain networks, which in simple form are the normal players associated with declarative memory as a whole. The first high-density EEG studies in humans described slow oscillations as negative waves that originate in frontal brain areas, and they travel posterior, following the major connectivity pathways in the brain. And this implies that the slow oscillations are global inhibitory downstates that travel across neocortex, possibly through the entirety of the declarative memory system. And this theory has lived on for about 20 years. However, rough and early attempts at source localization of these slow oscillations suggested that the source is more insular. And then later intracranial recordings of patients with epilepsy and also animal models showed that the generators were rather focal instead of global, and restricted to something like anterior cingulate cortex and medial temporal limbic cortex. And both of those results disagree with this very widely cited frontal posterior traveling wave theory. And so the point of our study was to investigate the source of slow oscillations during N3 using some new tools that we developed here in-house, and then do it in 10 participants in our own laboratory. So just to go over our study design, we collected all-night EEG from 10 adult participants. They were roughly 24 years of age, so just roughly college students, 6 males, 4 females. And they slept in the lab for a full 7 to 8 hours every night. And that was from about 10 p.m. to 7 a.m. And each participant had a T1 weighted MRI acquired so that we can construct a head model, and we'll go over those in a little bit. And then the blocks of N3 were identified using a convolutional neural network. And you'll see that when Evan gives his talk later in March, a kind of a deeper explanation of that neural network and what we use to classify our different sleep stages. One benefit of this neural net is that it only requires 3 channels in order to do the classification. So we'll go over slow oscillation identification. So the slow oscillations within N3 were first manually marked by following a specific criteria, which was each wave had to be greater than 75 microvolts, and then also fall within that 0.5 to roughly 2 hertz frequency band and be something like a frontal negative wave, as described in the literature. So each slow oscillation was marked at their peak in the frontal channels, and then they were subdivided into topographies based on the earliest channel where the slow oscillation reached its peak. And when we did that, you could get slow oscillations originating in a variety of different areas. You'll see that they're kind of more restricted to those frontal areas when we actually go through the data, but just for completionist, there's all the areas that we were able to mark. And then the slow oscillations in each category were averaged on their peak, but bear in mind that the data processing was done at the individual participant level, meaning on average, like an average SO for each category was obtained for each individual. So basically, we did this analysis for every single person, every single one of their slow oscillations, and then we averaged that person's slow oscillations into those categories. The table shows the average number of artifact-free slow oscillations in each category per participant. You can see some categories were more frequent than others, like I said earlier, namely frontal and central categories. Note these are like really low numbers, but the slow oscillations are very large amplitude components, and they require almost no averaging to get a decent signal to noise ratio. In fact, we've done quite a few single slow oscillation analyses, and the results are typically pretty clean. And then that moves us on to head model construction to actually figure out where the slow oscillations are originating. So once we had slow oscillations for every participant, we created a head model, and we used an in-house version of a head modeling software called Sorcerer that allowed us to construct individual head models based off the participant's specific MRI. So recall from earlier, each one of these participants has a T1 that we collected before they slept in the lab. Sorcerer segmented 7 tissue types and allocates oriented dipoles based off the geometry of the cortical surface. Those are your source generators. And it generates a 3D volume of the scalp and brain and registers that or registers all of the sensors that they wore every night that they were in the lab to the scalp, so to the 3-dimensional scalp. So we're able to take a picture using photogrammetry of all of the sensors that they're wearing and then register it with their head model so that you have a nice representation of their scalp anatomy, their brain, and then the sensors in reference to that anatomy. So it's almost a model of that person's head while they're wearing a net. So it makes source localization just a little bit more accurate. And then we also have those oriented dipoles that tend to explain how current propagates from the cortical surface to those sensors more accurate than using something like an atlas model. From there, we assigned conductivity values to each tissue type that were determined by the literature, and then a lead field matrix was generated. And that lead field matrix is a matrix that describes how current propagates from the dipoles on the cortical surface to the scalp. And then it takes into account all the different conductivity values of the tissue types that it would either pass through or originate from as it goes to the sensors. An advantage of individual models over atlas models is that the individual model account for participants' unique convolutions or wrinkles on the cortex. Since we know the surface orientation, we can cut it up into these small patches and create a dipole or allocated dipole that is normal to that patch. This reduces a lot of ambiguity in the lead field matrix and allows us to be much more accurate. So to map from the scalp back to the cortical surface, which is just a fancy way of saying source localization, it requires an inverse solution. And for this particular study, we were interested in testing a new method called Bayesian multiple sparse priors. This is not my specific field of expertise. We have people in our house here that are much more kind of specialized in developing these tools. And maybe if you have questions about them, they can answer them for you. But essentially, it has a physical restraint where activity at the prior locations are smooth relative to adjacent dipoles. And this constraint is distributed sparsely with 400 local priors over all 2,400 dipoles that are typically on that cortical surface. In our testing, we found that this is more focal and accurate when determining sources compared to something that is more widely cited in literature or more conventional, like standardized Loretta or Loretta. For our study, we were curious to see if the slow oscillations were either frontal or they were limbic, meaning the source. And so after the models were made, each individual brain was mapped to MNI space, where it made it easier to identify and label Brodmann areas on each participant's brain. We hypothesized that the source of the SO is focally located in limbic areas, and so we subdivided all of our Brodmann areas into limbic versus non-limbic. And in total, that resulted in 28 limbic areas and 26 non-limbic areas. And the figure at the bottom to the right is a kind of a flat map or a two-dimensional view of a cortical surface that's kind of flattened out, so you can see the left and right hemispheres and see into all the crevices. And the different colors correspond to different limbic areas. So these are what we're calling our targets or our regions of interest. So we're hypothesizing that when we take each participant and we localize these slow oscillations, that with some certainty, they should fall more in these areas than outside the boundary. And each area has a different color, and then you have a huge map on the left there to go through all the different Brodmann areas for each participant. So we'll go through a few participants' results, and I'll just pick out slow oscillations that originated in frontal channels as they were most frequent and representative of pretty much all of the rest of the slow oscillations. But this is participant 1. Box 1 on the left, this is what a slow oscillation looks like in the field. So this is just what it looks like in EEG. View 2 is the scalp view of a slow oscillation at peak. And you can see that most of the negativity is over the frontal areas, and then the positivity balances out in the posterior. And you have this midline there that is more kind of central. View 3 and 5, it's kind of out of order. Not sure if you can see my mouse. No, I don't have mouse control. Dang. But views 3 and 5, this is a top and bottom view of the brain when we use multiple sparse priors to localize a slow oscillation. You can see on the dorsal view that you basically can't see any sources, but when you look on the underside, you can see these sources pretty tightly in more limbic or medial temporal areas. view 4 is a butterfly plot. And then if you were to compare views 5 to view 6, this is a comparison between multiple sparse priors, which we assume is more focal when you compare it to something that is more conventional, like S. loretta. So view 5 and view 6 are MSP, or multiple sparse priors, versus S. loretta. You can see that they have similar sources, but S. loretta is typically more diffuse. And then view 7 and view 8 are multiple sparse priors versus S. loretta also, but just in a flat map view. So one thing to point out here is that you can see a focal current source in right orbital cortex along with a right basal temporal pulse sync. So it's not necessarily purely frontal. And then also, if you look at the dorsal view, there's really nothing there. So moving on to participant 2, this is a source localization for frontal negative SO for a different person, showing a left medial temporal cortical source. And it's very similar, again, between MSP and S. loretta, but once again, MSP is very focal. And then here's a third participant, which shows a very dominant sync source distribution in right medial temporal area. And for this one, we're not doing an S. loretta comparison. I think you kind of get the hint of it, that MSP is very focal and S. loretta is more diffuse. But again, typically the main areas here are the same between the two. So moving on to our results, what we did is for each participant's N3SOs, we counted the number of times the peak fell within the limbic or non-limbic areas. And then we summed those over all participants. So basically what we did is we went through every individual and then every category of SO, and we took every single slow oscillation and we made either a check for limbic or non-limbic, and we summed that over all 10 participants and made a heat map to show where typically the slow oscillations were mapped at their peak. So this is only using the most dominant source. This is literally like the top 1% of activity for each participant and each SO. And they were localized to an average of 20.1 limbic areas per subject versus 9.6 non-limbic areas. And also understand that if this were a frontal source, you would see higher non-limbic areas. And this particular result was significant using just a simple t-test. So you might be like asking this question, so what about a frontal traveling wave? That is what has been cited in the literature for over 20 years. And so to test that, one good thing about Sorcerer is that we can run simulations. So here at the top is a simulation of what a frontal source for an SO would look like, and then a simulation of what it would look like as it travels posterior. Note that the inversion line is very close to the sources, consistent with the field patterns of a superficial cortical source. And then at the bottom, this is an actual 256 channel recording of a single, not average, slow oscillation of deep sleep for this same person, showing the head surface voltage topography and a source explaining this field pattern cannot be superficial. So in other words, the bottom is reality and the top is what the theory should be, that SOs are frontal traveling waves. And you can see that if you just compare the two middle views, so the top, middle, and then the bottom, they really don't line up. So this theory about a frontal traveling wave is really in question, because from what we see, these sources are, very dominant in limbic areas, ventral limbic areas. So some conclusions is that the source of slow oscillations are not superficially frontal and are not a global traveling wave. They are more than likely focal ventral limbic cortex, And this is very consistent with human epilepsy and non-human findings. And it suggests that limbic cortex contributes to these cortical downstage, which are very important for memory consolidation. Something also related to the study is that MSP is more focal than S-Loretta. Part of the study's goal was to test this new algorithm. And then past studies aimed at improving declarative memory through TES have targeted frontal areas during N3, but the current study suggests that if we want to target more limbic or medial temporal structures, it may yield better results for improving declarative memory during deep sleep using TES. And you'll see those results when Evan gives his talk later in next month. And that's all I had. So we're trying to stay kind of roughly around 20 minutes.
Thank you, Kyle. That was a great presentation. I just want to remind everyone, if you have questions, we'll go ahead and take them in the chat, and I'll go ahead and read them out. And we had a few questions that came in previously, so I'm going to start there.
Okay.
So I guess just to start off, what are your thoughts on why the slow wave localization found in your study differ from prior EEG studies?
Well, I think first of all, it could be just a misinterpretation. Just to start out, let me see if I can go back. I'm having a hard time transferring between Teams.
Oh yeah.
And this, every time I click my mouse, it wants to change. So if I were to play just this slide here, one thing that could be contributing to the confusion is at the bottom here. Recall, this is what it looks like in reality. So this is a slow oscillation from an individual that is just a single SO. If you were just to, interpret this at face value without paying attention to the physics of these sources, you may think just right off the bat that this source is frontal because most of the negative activity looks like it's frontal, right? And that's the origin of the SO as well. But the truth is that the sources of these waves and of these signals is a dipole. So if you interpret it from like a dipolar perspective, the source should be at the inversion line, which here is more in the middle. And when we do source localization, it's more ventral limbic. So one could be a result of simply not paying attention to the dipolar nature of these sources. But something else could be that we have more technology these days. So Sorcerer allows us to use individual head models, which are very accurate. Are you guys seeing this connection lost on my mouse? That's very irritating. Sorry about that. Sorcerer allows us to use individual head models and tessellates the cortex using oriented dipoles and is very accurate. And that's something that's kind of more last, 15, 20 years, I would say, is these new technologies, new source localization algorithms that give us more insight into where these sources could be. So, it could be a combination of a misinterpretation, but also, completely different technologies. But at the same token, you still need to do more testing, which is kind of the goal of the TES study that Evan will go over, mid next month, is actually targeting these and see if they have, a behavioral effect. If you target limbic, does it give you a better result for increasing declarative memory than if you were to just target frontal, right? You kind of just put them head to head and use that model.
Great. So this next question is coming from the chat. What is the reference for the intracranial recordings showing insular or temporal source of slow oscillations?
Ooh, I actually do not know, but I can send that paper.
Okay.
I'm not looking at the chat, but whoever that is, just send me their information. I can absolutely send that paper.
Yep, we'll do that. So I have some other questions. And it looks like Dawn
There
just.
you go. Dawn sent it. There you
Yeah, okay. Um, so a question about the participants. Did the participants feel the electrical current when it was first applied?
go. We did not apply electrical current in this particular study. So these are completely just overnight recordings. I think
Okay.
someone may be thinking about Evan's study.
Right.
Yeah. So no, everyone slept pretty soundly in this specific net, if that's what they were asking.
Okay. And another question we have are, what may be some functional implications for the laterality of the slow wave localization?
Laterality. So seeing that it's left hemisphere versus right hemisphere.
Correct, yeah.
So I don't know if we went over those results. So what we found in our study, and we didn't go over this, so I think this is more of a canned question, probably a naughty one from Dawn, is these slow oscillations were mostly generated in the left hemisphere.
Mm-hmm.
And quite honestly, everything would be speculative that I would give you as far as them being left versus right. Just being completely honest. I'm not sure if Don is on here, but if Don has his own little spin of why these are left, he could probably chime in a little bit more than I could. Don, are you on here?
I am. Can you hear me?
Yeah, go ahead.
Well, it is speculative. I mean, I think the most important thing at this stage is it was a pretty strong lateralization in these data. And I think classically, the object memory system, the ventral limbic system that is tightly regulated by the extended amygdala, is very important to the left hemisphere's language development. And in fact, many of these ventral limbic areas, like the temporal pole, as well as the superior temporal plane, are larger in the left hemisphere. So it may be an important clue that the consolidation in deep sleep is also left lateralized. And this will be interesting to follow up in the future.
Great. Well, I guess we're going to wrap up unless anyone has any final questions. Go ahead and type them in the chat. Okay, so why don't we see phase reversals of polarity with slow oscillations in the EEG? From what you're describing, one would expect to see frontal negatives or downstates, but phase reversing in more posterior regions. This does not occur in the scalp EEG.
So I'll give a comment on this question. Actually, you do see it in the scalp EEG.
Sorry, go ahead, Don.
And in fact, why don't you go through each of these participants? And the point is, if you have a mastoid reference, then you don't see it because you're using a biased reference. If you have a reference independent characterization, each of these scalp EEG waveforms shows a phase reversal. And maybe you could point that out in these particular subjects, Kyle.
I mean, you can see the phase reversal right here. So on the left, you have this huge giant negative, then you have this massive falling positive wave. It occurs immediately afterwards.
Well, and you can see so in this one, if I may, this is Fanlu, you can see the negativity at the top, and this is on the scalp surface of the person's MRI there. And the scale bar of the color is red is positive, blue is negative, and is scaled symmetrically. So the white line is the inversion line, the zero voltage potential line. So you can see the negativity is at the front, and then progressing back towards the head, The inversion line is around the frontal temporal region, and then it becomes positive towards the back and the bottom of the head. And if you step through a couple of these participants, you'll see that a similar inversion line with a positive voltage potential towards the back of the head. So you can see that in this case, in figure 2, and then at the same time point of the voltage waveform in 4. So a pretty consistent pattern of frontal negative, posterior positive with a inversion line, again, at the frontal temporal regions. Go ahead and step through a few more, just so people can see that pattern in some.
Those are the ones that we have. So this was,
okay.
Yeah, participant 1. We started on 2, so that was 3 different participants that it's
Okay.
all very consistent for. And these are very representative of all of our results across all 10 people.
Great. Well, I think we will go ahead and wrap up unless anyone else has any other questions for the Q&A. Go ahead and add them in the chat. Kyle, would you mind going to the last slide so that we can just preview Evan's talk, which is happening next month?
Yeah.
We have another paper that our scientist, Evan Hathaway, is going to present, and I believe that is March 9th. So just so you know that you'll get an invitation for the next webinar that's coming up. Yep, and so a question in the chat, absolutely, you can email us additional questions, you know, if you have other things that have come up. And we did talk about the other prior questions that came up, just so you know. And I just want to thank everyone for joining us today and participating, and hopefully we'll see you in the next webinar.
Hey, Corin, is there a place for people to get my email? I'm not sure if it was included in all of the media that went out.
Right.
But it would be a good idea to either enter it in the chat or maybe send it out to people in case they do have questions afterwards. Like, I'm more than happy to respond.
Okay. Yep. Let me go ahead and put that in the chat here. Yeah, feel free to reach out with additional questions, and I'll put the info address as well. Okay. Well, thanks so much, everyone, for participating.